Oh, shit.
Test.
Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Long since I've done one of these. I don't think I know what I'm doing anymore.
No, it's all good. It's all good. Hello, everybody.
Hello.
How are you doing? Let us know if you can hear us.
Yeah, somebody tell me you can hear me.
Yeah,
I haven't been in America in a while, so I don't really know what's going on.
So hello, everybody. Welcome to another Ask Us Anything about electrochemistry. Also want to shout out to Chris, who I guess closed on the house. I mean, you don't close on really anything else dealing with escrow.
I don't know. Maybe if a car escrow, is that a thing? maybe if you're driving like a $3 million car
Yeah.
You know, do you have escrow? Because it's like I imagine the insurance on a car like that must be terrible.
Yeah.
Think
Yeah,
about,
that's
you
right.
know, it's like if you get a little ding in the side of your like Lamborghini or something, it
Lamborghini.
probably costs like one of our mortgage payments to fix it,
Yes.
you know.
Yeah. Yeah. Let's see. The title company, AG Property.
Silver property.
Silver
huh?
Property.
Cool.
Nice. You got a silver house.
Wow,
That's
that's I
fantastic.
mean that is
Chris.
that is expensive. It's
That's
made
very
entirely of silver. I
expensive.
mean, it's not gold, it's not platinum, but your property is made of silver. So I hope that you'll be using it as an electrode in your next experiment. Your house is a silver electrode.
Careful, it'll oxidize if you leave it out too long.
And if there's too much, like if you live somewhere where they put salt on the roads, it's going to make silver chloride. It's going to precipitate. Your house is going to precipitate.
Yeah.
So,
that's right.
we're off to a great start.
Off to a great start. All jokes aside, welcome everybody to another episode of Ask Us Anything About Electrochemistry. I'm Alex Parov. This is my colleague, Dr. Neil Spinner, and we're at Pine Research Instrumentation. And about every week, we try to answer any questions that you guys have about electrochemistry. So we get a lot of comments on YouTube and webinars and email and phone, and this is a time where we can answer your questions in a little bit more detail on a format that might be more conducive to whatever you're dealing with. So so as always, we are using Restream as the platform for broadcasting the live stream, and so we usually find that there's maybe a 20-second delay between when you write something in the chat and when we see it. So just keep that in mind whenever you're typing something. Usually we're in the middle of answering a question. So keep that in mind. If you do have questions, ask them in the chat and we'll get to them as soon as we can. Also, if you are a tier 1 or tier 2 member, there should be a link in the community post on YouTube that allows you to join us here kind of in the studio. Like you'll be able to share your screen, and that will be that'll be good. That'll be very that's a way you can share your data, talk to us instead of just typing everything. So that's one thing to keep in mind. We're gonna try. We usually go for about 2 hours, maybe 1 hour, depending on how many questions that we get. I know the school year is kind of starting and research is building up, so we may get more questions than normal or less. But we usually go for maybe 2 hours at max. Lastly, there are no dumb electrochemistry questions. We have noticed over time that the clearer you can make the question, the better we are at answering them. So we may also ask you for more clarification in the chat for if we don't fully understand what you're asking in the question. So keep that in mind. And then lastly, we may mispronounce the YouTube names that you have. Some of those names may be your name, but they may also be Pokemon. They may be whatever. So apologize in advance of that, just in case.
I think that's a good caveat, though. We're mispronouncing YouTube names.
Yes.
These aren't real names. Like Chris, that's obviously a fake name.
Yeah.
Nobody's named Chris. That's not a real name. So like we're mispronouncing a YouTube name. It's just a bunch of random letters and numbers. So I don't feel bad.
Yeah.
I mean, you shouldn't either. I think.
Yeah. We also get much easier names to pronounce, like Georgie.
So Georgie is totally fine, but like Tris, like
Tris
I just,
it's hard.
How are we supposed to work with this?
Yeah.
Like, give us, you know what I mean? It's totally fine. Okay, so. I'll just say briefly as well that for any watching now or watching the replay that I was for the last couple of weeks. I think I was in the airport with you.
Yeah, you were in the airport. One of them.
I was on my way to France for the ISE International Society of Electrochemistry meeting that was in Lyon, and if anybody, I saw many people stop by the booth who told me that they watch us incredibly on this electronic platform through the internet tubes. So thank you everyone who stopped by the booth and met with me in person. It was really nice to meet many of you and put faces to the ridiculous YouTube names. And it was really fun. Anyway, I love France personally. Just it's my own personal thing. So anytime I can get out of America and go to France, I will take that opportunity. And then I was in England for the UK Electrochemistry conference in Bristol, and a little bit of a smaller conference, but to anybody who came to both of those conferences, it was great to meet you in person. And thank you for watching our stuff. Very, very nice.
Nice, nice.
So do you want to start with Windstar's comment? I think you have
We
some.
can. We also got a question
Yeah, maybe we'll answer
that
the
just
live one
came in.
first.
We'll do the live one first.
Yeah.
I did also forget to mention that we will have in the description of this video, if you're watching it after the live stream, with timestamps for the questions as we go through them. But we have a question from Mawish Salim. Hi, can you please tell me that how can I choose an electrocatalyst for water splitting? Well, there's many. So I think one thing to keep in mind is really, I think, to define water splitting. There's actually a lot of different parts to converting water, H2O, to things like oxygen and hydrogen. Some catalysts do one part of the reaction, some catalysts do the other part of the reaction. It depends on the electrocatalytic system. But I don't know, aside from looking in the literature for what's been done, it's all platinum stuff.
Well, yeah, I mean, honestly, like the short answer is platinum.
Platinum.
There you go. Next question. No, I mean, platinum does so right. So generally speaking, when people talk about water splitting, they're probably referring to the production of either or both oxygen and hydrogen.
Yeah.
Right. So at extremely positive potentials, water with an electrocatalyst and salt, some electrolyte, you will produce oxygen. It's called the oxygen evolution reaction. And at extremely negative potentials, comparatively speaking, you will produce hydrogen, which is called the hydrogen evolution reaction. And so this is one way, for example, that like when I was in graduate school, even, which was at this point like 62 years ago, we had a system that supplied the research center with hydrogen gas. You know, if you're in a laboratory now, which you probably are if you're watching me, unless if you're not, why are you watching me? That you probably have gases. Maybe you have one of those big gas cylinders next to your lab bench, but some facilities, I was fortunate enough to work in one that had like a nitrogen line, I think an oxygen line, and a hydrogen line, which is really cool because it's like they're plumbed throughout like the building, and you just have to basically siphon with like a valve or something, right? When you want to, so if you're doing electrochemistry and you need to do like oxygen reduction reaction, you just get a tube from the oxygen line and do it. You don't have to like find a cylinder and do a whole thing. So anyway, all of this is to say that we had a system that was basically a glorified water splitter. It was a big giant box somewhere in the corner of the facility that produced hydrogen by splitting water up, presumably by applying a very negative potential with some stacks of catalysts. I assume they were platinum, but I don't know exactly what they were, of course. And it produces hydrogen gas. And there must have been some other stuff to the system, like purification processes, or I don't know exactly what. In any case, that's, what the process is. And so that's splitting water up, of course. And if you're producing hydrogen on one electrode, you're going to be probably producing oxygen on the other one.
Yeah.
The thing about that is the answer to your question, I suppose, is like the short answers are, like I said, like no joke, platinum, ruthenium, mostly noble metals tend to do these reactions pretty well. Right. And they're expensive, but they're inert. Like they don't change over time too much themselves. So they'll continually catalyze. They'll eventually get poisoned or something like that. But they're good options for that. But otherwise, the answer to your question is like Alex said, like look in the literature, like that's how do you choose a catalyst? Like everyone's trying to choose a different catalyst because they're trying to replace platinum because it's expensive and not ideal to have to continually use really expensive or difficult to obtain materials for these processes. So, the answer to your question is what like a huge amount of researchers in electrochemistry are doing all the time. Well, I'm going to try to use this, transition metal oxide or whatever, right? Because you're trying to find an alternative for some of the noble metals.
Yeah. And actually, there was one thing you said that I thought was good, is you can use metals that are good for water splitting, like platinum, iridium, ruthenium, stuff like that. But you can also use stuff that's bad too, like use glassy carbon.
Yeah.
Like just to figure out what a bad catalyst looks like.
You'll
and-
get some if you go,
yeah,
you know,
if
enough.
you go high enough.
If you go,
can
if
get
you go
some.
high enough, you'll also start oxidizing the glass carbon itself, which is
Yes.
which is just great.
Yeah. So so those are kind of our suggestions. We don't have a we don't have any suggestions for how to choose it. Like, if you have a system already in mind and you're trying to figure out like how do I iterate on that, please let us know. And if you have any follow-up questions, please.
Well, actually,
please
the
let us know.
follow-up questions from Peter here, which kind of leads
Yeah.
pretty well into, I don't know, a follow-up, if
Yeah.
you will, because Peter
Mhm.
Peter says, any suggested resources to get started with practical electrochemistry? I'm a chemist, a master of science. I think that's what MSc means, right? With no real
Yeah.
electrochemistry experience and about to start a hydrogen fuel cell project, so biopotentiostat, etc. Right. Well, first of all, what I'll tell you, which maybe it's still, maybe it doesn't mean anything, but if you are concerned about the fact that you don't have a lot of practical electrochemistry experience, join the club. Okay.
Yeah.
And I really mean that, actually. Almost everyone who starts off in graduate school or starts doing an electrochemistry project, whether it's a full PhD or it's a master's thing or whatever, does not have much going before that. It's like electrochemistry is this odd subset of chemistry where it just seems like there's not a lot of stuff covered on it before the graduate school level. And there are exceptions, of course, but not many. So the first thing that I would tell you is, like, don't feel bad.
Yeah.
All right, next question, everybody. No, okay. So practical resources. I mean, honestly,
I would also have a question
Oh, yeah.
because Peter, maybe you can elaborate a little bit more. You say you're about to start a hydrogen fuel cell project. That seems very broad.
yeah, you're
in
trying
my
to develop
mind,
like a different catalyst for it, or you're just studying PEM fuel cells. Just so,
Yeah.
so if you're gonna
are you making a catalyst to convert the hydrogen to energy, or are you trying to generate hydrogen gas? Like,
hydrogen
I mean,
fuel cell,
if it's a fuel cell, I imagine he's trying to make the catalyst that takes the hydrogen and turns it into energy.
well, that's possible, but at the same time, that's the anode of a fuel cell, and the anode doesn't require a lot of research anymore. People are only studying the oxygen evolution reaction for a reason. It's the rate limiting step in a fuel cell. So that's why everyone's studying ORR, not hydrogen.
Yeah.
The oxidation.
Right.
It's not hydrogen evolution. But in any case, it seems like you're just talking about you're starting a fuel cell project. So
Yeah.
I mean, suggested resources. Yeah, I mean, it's tricky, right? I think the project involves a new catalyst on a rotating electrode. I mean, you're right in our wheelhouse
Okay.
here, man. This
Yeah.
is this is what our company makes here.
Yeah.
Without being like, well, listen, do I have the product for you if you'll step right up into my office? I mean, you see these pictures over here? That one, the closest to Alex.
It's hard. There's a little bit of glare.
Yeah,
but,
it's a very artsy, oddly grainy, zoomed in picture of our MSR rotator.
we should change these at some
I'm trying to
point.
think, like, what's the best, like, practical. Honestly, like, everyone gets in the lab and just tinkers with it. Like, practical. Well, that's part of what
Well,
we're doing
if
here. We're trying to keep
If you're
practical
doing like a
stuff.
rotating disc electrode experiment, like, I would start personally. I would start with first, like, familiarize yourself with your bipotentiostat, your rotating disc electrode, and just, can you reproduce ruthenium hexamine or ferrocyanide on a rotating disc electrode? Like, just get the electrochemistry to work. And those are well-behaved electrochemical systems. Like, can you just do a basic CV or a basic RDE? Like, that's the thing to start with. And then you can look at, okay, like, in the literature, in like a textbook like Bard and Faulkner, do I get something like that? Can I reproduce this experiment? So whenever starting any kind of project, in my opinion, can you reproduce a somewhat well-characterized system?
Yeah.
Approximately. And then the research part is like, all right, well, I changed the well-characterized to an not so well-characterized system. And that's how I start my research.
Also, I guess even backing up before that, like, I'm just thinking about, you're trying to start like a fuel cell, trying to look at a new catalyst on a rotating disc electrode. Like, first of all, there's so much to that. Like, there's a lot of steps
Yeah.
involved. Making the film itself, on your on your electrode, your rotating electrode. Like that's a whole thing in and of itself. I bring up this name whenever this comes up because he's a kind of a friend of mine and also someone I respect tremendously, who's done a lot of work in this topic. His name is Yannick Garcini. He's at the Naval Research Laboratory, and it's at this point, however many years, like 10, 15 years ago, but he has a series of papers I highly recommend on just making that film. Like he's one of the only electrochemists I know, and there may be more for sure, but like I said, I know him personally, so I always vouch for him. He's written papers, not even just on like how the ORR works or whatever. It's like how to make the film on your rotating disc electrode. And there are strategies therein. And it's really like more arts and crafts than science, but basically, I highly recommend Yannick, Yannick Garcini, Garsany. I can type it into the chat as well. Find papers by him and you'll get some tips on making the film itself. But really, again, to back it up, even before reproducing something like ferrocene, where you would like oxidize it on the disc and reduce it on the ring with a bipotentiostat, all that kind of stuff. Like if you don't have a lot of experience with electrochemistry at all, like in and of itself, like you need to probably spend some time familiarizing yourself with whatever potentiostat and software you're using, with the rotator itself. Like you might have to take like a week or pick a time frame. I mean, I don't know exactly. It depends how proficient you are and how much time you have, I suppose. You're going to need to spend some time doing like really basic stuff before you try to get answers of what you're actually looking for, which is like, does this catalyst work for a fuel cell? That's like 3 levels downstream from where you want to start. Like my advisor, when I started graduate school, basically one of my first several times in the lab is like, he showed me how to set up an electrochemistry experiment. It's like, you have a glass cell, put some sulfuric acid in it or whatever. You know, here's how to clean afterwards. Here's how to polish the electrodes. Okay, well, now you got to set up your experiment. You got to put working, reference, and counter. Here's how to connect it to the potentiostat. And basically, I used like a platinum disc, and he like, you know, showed me a image, or I looked up, you know, in a paper or whatever, like what the typical platinum CV looks like. You know, most of us know what the platinum, let's just say platinum and acid CV looks like. Has a pretty distinctive shape and features to it. And it was like, go give me that, you know? And I was like, oh, well, no problem. And it was like, I did it and it looked terrible. And I'm like, oh, why does it look terrible? And it's like, just give yourself like a week to like make one platinum CV look good. Like not rotating, just the tip. Like, I know it sounds very rudimentary and simple, but it's like, you're going to learn a lot of things about electrochemistry practically by just trying to do this very one simple step. And you're going to mess it up a lot, even though it doesn't seem. There's a lot of little things that you're going to learn as you try to do that. So it's like, before you start making a film and trying to do all this stuff, just pick one very simple electrochemistry task and try to accomplish that. That would be my like stage 1 advice before all the rest of it. And then as you go, keep coming back here and ask questions seriously. Like next week, if you've done that or something and you're like, hey, listen, I'm having trouble making the film, come back and ask a question. I know a lot about making films for these things. I've done that a lot as well. I know a lot about oxygen reduction reaction and things about fuel cells. You know, as you do this, feel free to come back, ask us questions about it. We'll try to kind of guide you through that. But a lot of this is going to require a lot of time from you to build up the competency of even the most basic electrochemistry stuff, because it's hard. Okay. And it is going to take a lot of your just repetition, I would say.
Yeah. I agree. All right. Looks like Race has a question specifically for you.
Oh.
Race is saying, Neil, I heard in your lecture that you could delete inductance effects at high frequency during EIS. However, to my knowledge, we should not delete it as it gives unreliable readings of extracted values.
You heard wrong. First of all, Race, welcome back. Listen, if there's one thing you can count on me being here, it's to give you just terrible, like quippy little, like I'm a character in a Marvel movie giving a quippy, you know, like, right, like that was
like
every
comic relief.
Yeah, like no, but it's like that became the thing, to the point that like in the more, after however many movies, people were like, all right, enough of this. Can you like pick a different shtick? You know, it's like,
be a serious
it's
character.
like Tony Stark would just be like, oh, that's a terrible plan. Anyway, You know,
Yeah,
like just like
yeah.
everything was a quip,
Yes.
and then they move on, which it was funny for a while. I still thought it was funny. It's probably why I keep doing it. First of all, I also just want to mention, Race, you sent data like a long time ago, and you sent it in a file that I couldn't open. I asked you for a different format, and I hadn't heard from you since. So if you're still looking for me to do some analysis of some data that you had collected, let me know. And maybe you didn't get my email. It might be one of those, like, you call it like phone tag, like you sent me a thing, I sent you a thing, and both of us thought we were the last one or something. As far as I was aware, I was waiting for you to send me the data like in like just a CSV or a different format, or maybe I needed the frequency call. I can't remember exactly, but anyway, feel free to email again if you want some of that analysis, because I was waiting for you and I hadn't heard back, and then I traveled for a month and I don't know where we're at. So okay. To answer your question, if the high frequency inductance effect is a loop, Alex's favorite thing. Let me.
Well, no, he's not talking about inductive loops. He's talking about
He said high frequency inductive effect. Okay, he could be talking about a loop, so I have to talk about it.
No, he could be talking about a high frequency induction in the cable
Okay.
at high frequency, not mid to low frequency.
I'm gonna need you to breathe slowly. Breathe in.
Just saying, it's probably not. He's probably not talking about.
I think he might be. He's probably not.
No.
Just
go
for the sake of
ahead.
argument, there's one kind of inductive effect if you're talking about this, right? Let's just say I have like the most basic data here. This corresponds to a circuit that is like this. Okay, there's an inductor, there's a leading resistor, and then I'm just going to even simplify it. I won't even use a CPE. I'll just use I have my hand raised like I'm asking a question. Yeah, you. Yeah. Call on me, please. And you probably can't see me because the camera is small and you're watching my amazing artistic ability. Okay. So this is L. This is R. I don't know. I'll call it R0. I usually call it R0 and R1. Ohmic resistance, uncompensated resistance. We'll call this C1. All right. So this, let's just, in like the most ideal situation, let's just call something like this. Okay. This is my inductance. This distance here is my R0. This distance right here. Oh, I didn't draw this circuit right. If I erase, the whole thing goes away. Forget about this tail.
You can.
I didn't draw the tail. I drew a tail. I didn't draw it in my circuit because I'm stupid. Okay, so let's just pretend this is just a semicircle. I was going to draw. Forget about the Warburg because it won't affect how I'm going to answer your question. Yeah. I didn't mean to complicate things. So the first answer to your question is, if this, as Alex hopes, if you have just this tail here, I shouldn't draw it dotted because this is like your data. It actually dips below here. Okay. And you have inductive stuff where it dips below on the Nyquist plot, right? This is minus Z imaginary, and this is Z real, and this is 0. So essentially it's like negative. Then let me see your question so I can word it. You said that we should not delete it as it gives unreliable readings of extracted values. That is not correct. Whether this is here or not, these results will be unchanged. In fact, let me show you another way in our software. Okay. And I guess I'll spare Alex. So what I'll tell you is that if it's an inductive loop, like if there's inductance in some manner that's like incorporated, like there's a loop after the beginning, whatever, then you are correct. If there's some inductive behavior that is not what I just showed, and it's sort of manifesting in a different way elsewhere, then yes, you cannot like remove it, as it will impact the calculation of the rest of your parameters. Circuit simulation. Okay, let me share this fancy thing with you now, and I'll show you. So hopefully you'll believe me. Okay, I'm going to show. Where is it? This one. Okay, and you can't see the selector. All right, you see this? You see this? This is what I just drew, but now it's actually in our software. All right, perfect. So here's the point here. All right, I have this leading resistor is the uncompensated resistance. It moves it left and right. right? The width of the semicircle is like the charge transfer resistance that makes the semicircle bigger or smaller. Okay, those values are what they are. Now I can change the value of this capacitance, and basically it will change. Now I should also clarify for a second. It is possible, depending on the value of the capacitance, that inductance could affect things. But for the most part, the situation that you have is one like this. You see how changing this inductor value just makes it dip down farther? Now, if the inductance value does, I will admit, if you have a shape like this where it starts to get, there's blending or something between the, I hope you, I mean, you can see what this part right here, right? It's not like straight up and down, right? There's kind of like this blending between the semicircle and the inductance part. Then it is possible that by neglecting the inductance, you would potentially impact the measurement of the capacitance, and only the capacitance for the most part, not as much the resistances. But most of the time, the reason I say that is because of this phenomenon. It's mostly that the amount of inductance you have when you have a cable inductance like this, something like that, and you have okay, two things. First of all, the amount of inductance you have with a cable inductance or whatever is not that high, right? And so basically to neglect it, it's like if it's not there, you just get this, and the values of my capacitor and my resistances are unchanged entirely, right? All it's doing is making a little bit of this initial tail drop farther or not. So removing it has no impact on basically on the calculation of my other values. That's the first thing. And the second thing is that in the systems where you have this kind of inductance, a lot of times batteries are the easy example. A lot of batteries, you do like coin cells and things like that. They are characterized by very, very low impedances, like milliohms, and very high capacitances, like millifarads to farads, very high. So even in the case where, like I said, I did admit and acknowledge that if these values are close or something, if you have a really high inductance, like this is a ridiculous amount of inductance, like no cables have this much inductance. Look how far this line goes down. It's ridiculous. I can't even find the end of it. In fact, it drowns out the semicircle. There it is. I found it. Okay, great. So like there's no system that really looks quite like this, and correct me if I'm wrong. If that's what you have, then my apologies, but I doubt that. And then the other thing again is that with a battery, because the capacitance is much higher, typically it negates that. Like it's like you have to have a really high inductance and a really low capacitance for those things to blend together to the extent that one affects the other. So hopefully this is a relatively quick but visual way for me to show you that in the case where the inductance exists here, you can just sort of, and by the way, just to be clear, it is not exactly and I doubt I said this verbatim, what is it? You said should not to delete inductance effects. I never advocate for deleting data that's unethical. What I advocate for is neglecting or omitting certain parts of data from certain analyses. That's fine, but I do not advocate for deleting data that's like scientifically unethical, to like just pretend your data is not there. Like your data is what it is. Mm-hmm. That's not the same thing. So to be clear, I hope that addresses that scandal in my previous. He's talking about deleting inductance. Listen, I was doing it in solidarity of my colleague here who hates inductance. He doesn't believe in it, and I support him.
I need to learn a little bit more about it. I've been looking at this book, which you probably can't see.
Is that Orizum's book?
It's Mark Orizum's book.
Yeah.
Which is called Electrochemical Impedance Spectroscopy.
It's one of the only like
second edition
EIS books. There aren't many. Lazia has one, and then Orizum and Triboulet and what is it? It's Triboulet, Orizum, and what is it?
Yeah, Triboulet is Bernard Triboulet.
Is it just those two? Yeah,
it's just two. Yeah,
there's a few other people who've collaborated with them, but in any case, Jogni says, how was the Bristol Electrochem conference? It was good. It was really, it was actually, I've gone to it 2 years in a row now. Last year was in Edinburgh, and this one was in Bristol. So yeah, it was good. It's a shorter conference, like 2 days. But it's cool. It's one of those conferences where it's like there's not like the ISE conference in France was huge. Like it's big. It's a big conference, so it's quite busy, and it's a whole week. This one is like 2 days, and it's one of those conferences like everybody's sort of together for most of it.
Yeah.
There's a few different disparate sessions, but it's not like a major conference where there's there's 15 different sessions at any time and all this stuff. And
Yeah.
so in these smaller sessions, everybody's kind of together. So when people are eating at the coffee breaks and at the whatever other sorts of events, everybody's kind of all together. It was a cool tour of the SS Britain or something. It's a boat that's they have it sort of as it's almost like a museum now in Bristol.
It's like a World War II boat or something.
I don't think no, it's actually older than that. It's
Oh.
yeah, it was in the 1800s. It's been decommissioned for a while now, and for 100 years it was about. See, I really paid attention. You can tell. It was for 100 years that it went all the way down to the other the tip of Africa. And it was part of some exploration stuff, I guess. I don't know, but
okay.
we walked through it. It was kind of neat.
Interesting.
So
Cool. Cool.
Yeah. So there you go.
Excursions.
Yeah, we did a little bit of excursions in Bristol. So
Nice.
anyway,
we have a question from Andrew Rodriguez. How important is picking a correct electrolyte to test a supercap in EIS and galvanostic charge discharge, etc.? I feel like it's probably pretty important, considering that, well, not that I know very much about supercapacitors, but the electrolyte can make a big difference. The concentration, the type of electrolyte. I do think that it will probably make a reasonably significant difference in the data you get for EIS and galvanostic charge discharge. So you may have to do a little bit of playing around with your system, which electrolyte to use, whether it's aqueous or non-aqueous or supporting electrolyte salts. You may need to play around with it. But I don't know about what problems you might run into if you picked a, quote, incorrect electrolyte. I imagine the capacitance would change a decent bit. But
I mean, I think that the capacitance, yeah, that'd be a problem if the capacitance changes appreciably with electrolyte, in a sense, because if you're trying to study the properties of the supercapacitor material, I think the short answer is that it matters.
yeah.
The longer answer is that in general, you can pick whatever someone else did or whatever. This is just one of those things that's if the goal of your particular research is to study the material,
Mhm.
then your job is probably to find some papers and enough of a quorum or a consensus or whatever you want to call it, where people used something state of the art or whatever, because you just want to pick something that everyone else is using that will probably give you the most consistent results to compare with. If your task is, on the other hand, to optimize the electrolyte specifically, in addition to or as its own research topic, then you're going to be doing a different kind of a study. But it's in general, it's not that it doesn't matter, but in some sense, the answer is that it doesn't matter. Is that you're just going to pick, for your project, right? Like I did battery. Okay, so I just as my own personal, I did battery stuff when I was in graduate school, and there's a lot of people studying the membranes and the cathode and the anode and the electrolyte. And people study the electrolyte. They study like ionic liquids like TFSI, and they study different carbonates and different mixtures of carbonate salts and whatever. And it's I wasn't studying that. I was just studying anode materials. So I just found that a 1:1:1 ratio of ethylene, dimethyl, and diethyl carbonate with 1 molar LiPF6 is what a lot of people use. So I just used it. Did that impact my results? Had I used a different ratio? Probably, maybe. I don't know. I don't care. I just used something that would work and was roughly equivalent to what a lot of people are using, and is roughly equivalent to what modern commercial batteries are using. And so when I'm comparing, for example, anode material 1 versus anode material 2, I use the same electrolyte in both of them. If I had used different electrolyte, I would have added a different variable to my system. But I didn't really care about that because I wasn't trying to study the impact of electrolyte. I'm trying to study the impact of other stuff.
Yeah.
So I guess that's the answer there, is that it matters, but for your purposes, if you're not studying the electrolyte specifically, pick one that most people are using that's verified in the literature, and then effectively it doesn't matter. Unless you run into problems, and then that's a whole different thing. If you're troubleshooting and you think the electrolyte is causing your problems, that's different.
Yeah. Looks like Barry. Barry, good to see you. Says, in Aftermath, is there a way to default showing the current voltage during peak position? It's a lot of extra clicking. Well, we know our software always could use some improvements. Although I don't know exactly.
It does that now.
Maybe what version, but like I have. Oh, do you have Aftermath up now?
I was just going to show them. It actually does that now.
Yeah.
The problem, Barry, is you're using a version that's not the most recent. So there you go. It already does it. So the problem is that I actually don't know without looking a little further or talking with our software manager. Like, this is any software. There's some version whereby it didn't, and now it does.
Yeah.
Right now it shows peak height and peak position. It didn't used to. And yeah, you have to double click here. Basically, I know you probably can't see the pop-up window. I have to it's a weird thing about this screen sharing thing.
Oh yeah.
I wonder if I can share just the window. I guess the pop-up window. Yeah, this is the pop-up window that showed up. Right. So here's like the properties, and then it's like peak tool property. Where the heck is it? It's I don't
Peak
even,
tool properties upper right.
I don't even remember. No, I know, but there's a show peak position here. So it's like unit visible, right? Something like that. Peak position. This is a newer version too. This might not look familiar to you. So some of these things, but these, when you double click on it, you'd have to like show it. I don't have to because it's automatically, it shows it now.
Yeah.
And this is also a blue version. You're probably using a green version. Anyway, the short answer is that if you really want that and it's bugging you a lot, please email us. We can probably get you a version that it's automatic in. We did update that, and you're just using too old a version probably. So we do actually pretty, I don't know, often enough update our software. We're constantly working on it, but it's just a matter of what has high priority and what gets fixed next. But that particular one, it's fixed.
Yeah. I think we'll have a blue version on the website
pretty soon.
I think it's going to be pretty soon. Yeah.
Yes.
Keep an eye out.
Shana Tova, everyone.
Yes. Shana Tova, everybody. It's Erev Rosh Hashanah.
Is it tomorrow?
Well, tonight.
It starts at sundown. Is that right?
Starts at sundown tonight, and then tomorrow.
Yeah.
Is services and all that jazz. Let's see. Prosperity S. Prosperity S. What information LSV graph can give me? That's right, because G and H are next to each other.
They sure are.
Yes, I can easily see that as a typo. But well, in general, there's a lot of information that can be shown on LSV graph, and I think my thing's showing up. So you got your voltage, you got your current, and the applied potential that you're doing is something like this. So if this is time and this is voltage, you're doing something like this. So this is your linear sweep voltammogram, and then your current response might look like something like that, right? I always think about linear sweep voltammetry as just a part of a cyclic voltammogram. So you're getting current information, which is usually indicative of, say, the rate of a reaction. It's also indicative. You can get some thermodynamic information based on the potential, the electrochemical potential. You can get things like, for example, if this is part of a cyclic voltammogram, which actually looks kind of like almost an RDE, but you can get like the E naught or the E1 half based on the voltage position. The peak current is typically used for determining things like the electroactive area or the concentration of redox species in your solution. It, of course, will depend on what system you're looking at, right? If you're studying a battery versus a 3 electrode system, with solution phase redox species, or if you have coupled chemical reactions and stuff like that, the information that you get is going to be very different. And of course, you can always change the voltage applied as a function of time through, say, the scan rate. So there's a lot of information. There's a lot of information that you can acquire from the graph. It really depends on what exactly you're trying to look at and what you're trying to study and the system, and then what variables you want to control or change. So that's kind of what I would describe as a short answer for what information an LSV graph can give you. But Prosperity, please let me know, or let us know, if you have any further questions or clarification on LSV. All right.
I think there was some follow-up
Mm-hmm.
from Andrew. He did. Here it is.
Yeah.
I know that Chris was also talking a race. There was some back and forth here, but you say you did GC, did galvanostatic. That's the word. Charge discharge on CO304. I think that's a spinel cobalt oxide. Curves were blocky, vertical charge and discharge lines, and flat in between. Does this mean the material sucks at charging? It's not a dumb question. The answer is yes. It does mean it sucks at charging. Something is wrong. Something. One of two things happened. Something with your experimental setup wasn't optimized or right. This can happen, or the material is terrible. To the best of my knowledge, not a lot of transition metal oxides can function as supercapacitors or battery electrodes. Not all, though, and not every morphology, for example. So I know that like cobalt, for example, can be in multiple oxidation states, right? So like COO2, for example, is like 4+, right? And that one is different than CO304 as a different oxidation state. So anyway, the point of this is that like it's possible that this material isn't optimized properly. Again, it's possible as well that you might something with your experiment is a little wonky. You know, if there wasn't a proper interface, or there's 101 million different things that could be the reason. But if that's what you're getting for your results, it means whether the material itself or not sucks. You did not get a charge discharge like situation occurring. So why that may require further investigation, I think. Chris followed up on electrolyte permittivity will have an impact. You'll see surface coming. Yeah, again, I was like hedging here. I'm trying to say like, yes, it matters, but no, it doesn't. It isn't to say that the electrolyte, again, just to reiterate, it's not to say that the electrolyte doesn't matter. It's just to say that if you're not trying to study the electrolyte effects, find one that you know works based on literature and stick with it. And then you kind of just can mostly ignore its impacts, probably. That's the best advice I would give too, because frankly, if you're trying to study like the anode, whatever, something, or the cathode something, and the electrolyte's getting in the way, it's gonna convolute stuff, I suppose.
Race has some, I think, a kind of a follow-up with regard to neglecting inductance effects. Maybe he should have chosen better wording in his previous question. Maybe is there, but there is a famous example in the literature whereby neglecting inductance effects, authors have suggested a high DC ionic conductivity of a material. And then I think this is a follow-up, which is saying, please refer for, it must be, maybe it's figure 4, in composite effect in super ionically conducting lithium, aluminum, germanium phosphate.
Is that the title of a paper?
I think so.
Composite effect in super ionically conductive. I wonder.
Let's
composite
take a look.
effect in Super ionically conductive. What is it? I'm just trying to type it.
Yeah,
It's hard to copy.
yeah, it's
Ionically conducting lithium, aluminum, blah, 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 blah. Ionically conducting alumin. I'm just going to see if something comes up here.
yeah.
I should search on like a Google Scholar or something. Hang on.
Yeah.
Just going to do a quick little, what is it? Aluminogermanium. Aluminogermanium. I'm not getting, because that's because I can't spell.
It's a lot.
Did you find
But hopefully we can look at it. If you want, while you look at that, I can try to look at some other questions. And then
if you have a DOI, if that's a paper. So, I mean, the short answer, if you're asking about my knowledge of superionically conducting lithium, aluminogermanium, phosphate-based glass ceramics, the answer is I don't know anything. If you have a DOI that I can look at with a paper, I'm happy to look into that. And it's certainly possible that in this situation or this paper you're referring to, or something of that nature, that there's some effect of neglecting inductive effects.
Yeah.
Again, the difference, in my opinion, what I showed you is mathematically true. Whether that's the case with every specific system is another situation. Like for sure, I could be what I showed you, whereby like changing that inductive tail based on the values of the circuit that I was showing you just moves the tail up and down. That's just mathematically consistent. But that mathematical model might not apply to this situation, this system. Right? There's some other system might have a slightly different, set of parameters or situation that what I showed might not apply to. So, I would certainly say you might absolutely have a point, or whatever you're referring to could be a different situation, I suppose.
Yeah.
So do you know who T Witchy is?
I feel like it's Tarek. I looked at that picture and
How's
it's
it
like
going, my friends?
Yeah.
This is my good friend Tarek Bitar.
So what is the settling time section? Is this an inside joke?
It's an inside joke.
Oh.
You're welcome, everybody. Congratulations. Everybody gets to witness our inside jokes. I just spent some time with Tarek in France. We had a good time.
That's good.
Yeah. Yeah, I put my phone down. I can't stare at my phone and I can't talk to you through the camera and on my phone at the same time. All right. What do you expect of me?
Oh, he messaged you.
He's texting me about germanium alloy, tin something. I don't care. I think I can. I'm just kidding. He's trying to disrupt my live stream.
No.
That's what he's doing, even though I invited him. I invited him to disrupt my live stream, and that's what he's doing. Exactly.
Yeah.
Because you know what? I don't really care. It's fine. This is fun. Hey, Ferris, welcome back.
Yes. And Ferris has a question. Is it correct to use cyclic step chronopotentiometry to do charge discharge battery cycling in aftermath? I'm not seeing any specific GCD experiments running into memory. It's just trying to do a long-term cyclic step chronopotentiometry experiment.
That's one option. There's a couple options, Ferris. I'll kind of show you a few things.
Yeah. So I think I get this. Sometimes I get this question too. I'm like, I don't know exactly what the best technique is because we don't name it GCD. That'd probably be very helpful if we just named it GCD.
Well, we're getting there. So first of all, as you can see, and this is a newer version of Aftermath you probably don't have, but we have some battery techniques like pit and git. It's like a version of charging and discharging, but you have a couple of options for doing charge discharge stuff. Okay, so cyclic step chronopotentiometry or cyclic step chronoamperometry. Those are options. You can also just do chronopotentiometry and chronoamperometry in a sequence. So something like, if you want to do this one, could be like charge, and then I'm just gonna like quickly make a thing to kind of give you a discharge. So let's say my charge experiment. I'm gonna get rid of inductance. Excuse me, induction
period.
Inductance, yeah.
You removed the inductance from the battery.
I did. See, I removed the inductance, but everything's just fine. I told you it's useless. All right, so let's say my charge is 1 milliamp for 1 million seconds, and my discharge is get rid of inductance again.
This
and then
means it's a little bit
relaxation.
bigger.
And then my discharge is minus a milliamp for another million seconds. Okay, whatever. So those are my like charge and discharge, galvanostatic charge discharge steps. So what I could do is I could do a sequence and just drag these in here. There's my charge and discharge, right? I'm doing one of the, I could do this for 150 times or 1,000 times or whatever. Okay, so that's the first answer to your question is you don't have to just use cyclic step or whatever. You can do these, they would do it this way. Okay, and there's some benefits to doing it this way, which I'll explain in a second here. As far as memory issues, of course, some of the problem is on the computer. There's not much I can do about that. But of course, sometimes if you have a very good computer and the software itself is filling up a lot, you can do a couple things. You can change the number of intervals. If you do one interval, it won't fill up. You only get 1 point. That's pretty terrible. I get it. The point is you can reduce the number of intervals. Now, if you're doing like 1,000 cycles, odds are you don't need every single one of those cycles 100% of the points. So one thing you can do to sort of cheat the system here, I say cheat, I mean, it's like, it's not cheating, but it's, you can do like, okay, let's say you're doing 100 cycles. This is 1 through 99. And this is 100, right? So here's 1 through 99. I'm going to do this one 99 times. I got 99 charges, but interval ain't one. Sorry, I don't know. I'll be here all day for the terrible rap jokes.
I love
That's
rap
right.
jokes.
That's what you all show up for. Is electrochemistry related hip hop jokes from someone who doesn't really like hip hop music.
Oh,
Not so much.
disappointing.
I like almost every kind of music except American country and hip hop. I like some hip hop, like late 90s, early 2000s.
It depends what time frame it
I
is.
just don't like it all that much. I like
okay.
I like 60s music. Like old fogey music from before we were both born.
I don't know.
It's not that old. It's like that's like the gramophone, you know, like they have like the crank
Yeah,
music
yeah,
where they're
that's
like playing like like not that old. I mean, I'm not, you know, but I do like old fogey music. Anyway, sorry, what was I talking about? Yeah,
You're talking about
charge
charge
discharge.
discharge.
Yes. Okay. So, for example, if you're doing like 1,000 cycles, you only need like every 100 to plot, right? Because usually people will show charge discharge stuff like, oh, cycle 100, 200, 300, 400, whatever. They did 1,000. They show every 50, 100, every 500, whatever it is. Well, one way to not fill up the disk is to not take a lot of points on the ones you don't care about. So it's like you need to cycle it 100 times, but you don't have to collect all the points for those ones. You're not going to really look at them or study them. You just need to know basically like the first and last point to be able to get, you know, it's what its capacity was. And so if you do like even just 10 intervals over like an hour-long test, you'll still get where it ended up. Like you'll still get its final like the amount of time and the whatever.
Yeah.
You just won't have a lot in between, but you don't need that. And so it doesn't take a lot of points. And then on the last one, you can take like 8,000 intervals. Great. On the charge and discharge. So you can get like a full charge discharge curve for the last one. So that's one answer for like,
Yeah.
okay, do that. Now the other is this procedure called auto close archive. So here's one example. Here's 100 cycles. Let's say I want to do 200 or 300 cycles. Instead of adding, I could do this. So this would be like, right, the next set. This would be 101 through 199. Okay, and then number 200. Right, and then this I mean, this should actually just be one iteration, right? So I have 99 iterations and then one. And I hope you can understand how this works here, right? So I'm doing like 99 iterations with not much data collected. And then the last one I care about or whatever. The problem is that while I'm running this, all this is still on the disk. It's still here, right? This is one archive. Forget about these archives. Well, there's no reason why you have to run in the same archive. Make a new archive. Copy this here. Whoops, not that. What did I do? I put a sequence in a sequence, which you can do. You can embed sequences, by the way. I wasn't trying to do that. I just hit the wrong button. Okay, so here's another option. I do 200 here, and then this would be, I won't change all the numbers. It'd take too long. But this is 1 through 99 to 100, 101 through 199, 200. This could be 201 through 299, 300, 301 through 399, 400. When I click on this archive, if I go to File, you see that there's an option that says Auto Close Archive. Click that. Whatever other archive, Auto Close Archive. When I click the File menu again, you'll see this is checked, right? Okay. What I would do is I would run this and click. I don't have anything connected here, so I don't have an instrument. I'm just looking at the software.
Yeah.
But I click Perform Sequence, and it would jump to the live, whatever's happening.
Whatever.
Yeah, exactly. Just click over here. It's fine. Click Perform. Click here. Perform. Click here. Perform. Click to the next archive. It doesn't matter. You can send whatever to the instrument, whether it's in any archive or not. Like, you don't have to do everything inside of one archive. And click here, whatever. Click here. Queue up in order, like all of these things. When these first 4, in this case, have finished, this archive will save and close. It's gone. It saves to the disk. So you might want to like save as first, give it a location. Otherwise, it'll just save the default name, which is fine. It's just, sometimes saving the default name's a pain because you don't know where it saves. But what it's going to do is that when you're done running, Aftermath will be empty. And you'll come and you'll panic. And you'll be like, oh my God, all my data's gone. No, it's saved and closed. You can look at it later. But that means that as you're going, it's progressively freeing up RAM, right? It's saving and closing archives as you go. That can help. Mm-hmm. I think that's a couple of things that should hopefully help. The other that would help would be this version of Blue. If you're still having problems, Ferris, please reach out to me, because the other thing that's a subtle thing is that you're using a green version of Aftermath, most likely the current version. It's a 32-bit program. And this Blue version that we're releasing very soon, I mean, by this point in time, in however many weeks, it might be academic because we might have a version that's Blue as a whatever. It's a 64-bit version. Part of the consequence of that is that it actually has intrinsically, it's in and of itself, because it's 64-bit, it has a better like storage capacity somehow.
Yeah.
And
like
it's
a
like,
lot more.
Yeah, exactly. So the Blue version will be much less prone to running into memory issues than a green version, irrespective of what computer you're using or whatever. So,
well, if you have Windows XP, it's not going to work.
Well, that's, I mean,
if you have a 32-bit operating system, but hopefully you don't.
Yeah, most people don't have. It's like you can't even. Windows or Microsoft hasn't like provided updates for XP in a long time. So my guess is that most of you don't.
Yeah.
So if you have a 64-bit operating system and you're using a 64-bit software, which this newest version is, that will also help with these memory issues.
Yeah. In fact, I think I was talking to our software engineer, and he was saying like the whole auto like the save and auto close archive after it's done might not even be necessary for 64-bit. It has so much more. It utilizes so much more memory. Yeah. It might not be an issue, but we're not there yet, at least from a release standpoint.
Old Blue Eyes and the Rat Pack. I actually don't know Old Blue Eyes. I mean, Rat Pack is good stuff. Frank Sinatra, Dean Martin, Sammy Davis Jr. Fly Me to the Moon.
I know, it's just.
Am I just saying words that don't mean anything to you?
No. It's like my dad. It's like my dad, who was born in 1945.
It's more like your dad's music. It's like what this is.
Yeah, it's like my dad would call his friends in elementary school like the Rat Pack. Like
that's so
like that was the group of friends referred to them
was
as the Rat Pack.
Was Sinatra's music from? Sinatra was born in 1915. He died in 1998. Okay, so yeah, his music must have been like 30s, 40s. 50s, something like that, in that time frame. It's good stuff, man.
I know, but I'm the of the people in our office, I'm the most musically illiterate. There was at one point a picture of Lionel Richie on the
that was so board. Funny. Oh, that was so funny. Yeah, our boss put this picture of Lionel Richie. Well, it was the what was it called? Oh yeah, I'm forgetting.
All Night Long or something.
No, but it was. He put it. What was it was hello? It was hello. Because it was like one of these fake. People put like signs on.
Like if you've seen me, call this number or something.
Yeah, and you can rip off a tab and it's a bunch of the same numbers.
Yeah,
I wish I could find it. What was Lionel Richie?
But basically, he put this picture up on
I'm gonna
just
see
like
if I
our
can find it.
whiteboard,
He must have found it somewhere, like on the internet.
and you guys
The
were
only
talking,
person who didn't get it was Alex.
and I was just like,
Oh,
what is
yeah.
this? It's like, do you know who this is? I'm like, no. It's like, that's Lionel Richie. And I'm like,
This
who is
it.
that?
I think I found
And
it.
like, you haven't heard of Lionel Richie?
I
It's
think
like, no. Well, have you heard of this song? I'm like,
I'm sure.
you have to have heard this song. And they tell me the song name. I go into my office, I listen to it, and I'm like, I've never heard this song before.
Okay, I think this is it. Is this like?
Yeah.
Is this the
that's it.
Our boss just printed this out in our office. Just this is Lionel Richie, and he cut it. And it's just, is it me you're looking? It's from a Lionel Richie song. It's from Hello, I think, right? Yeah, it's from Hello. Yeah, is it me you're looking for? It's just like the lyrics of the song. It's a funny thing, and the only one who doesn't get it is Alex.
Yeah, I didn't get it.
Oh,
I
that's so
still didn't
funny.
get it. It's like,
That's so funny.
you have to have heard this song before. And I listened to it. I'm like, I've never heard this song before.
He's so not musical. It's so funny.
Oh,
that was hilarious. It really was. It was so funny. Oh,
Let's see. That was just an example. Okay, this is just looking at batteries. Do you plan on making a video series on batteries from electrochemistry point of view? It'd be highly beneficial to us.
Yeah, I would love to.
If we had time.
Yeah, well, first of all, it's
If
a
I
time
learned more.
thing.
Yeah, that's part of it.
So the second thing is that I'm hopeful within the year. I know it's like a long time frame, but our company is going to have a lot more like battery related stuff.
Yeah.
It's not that you can't, it's not that like we sell electrochem. I know we don't talk about Pine products all that much, but we're here to answer questions and do a thing. But like we sell electrochemistry products, and it can be used for fuel cells and batteries and all kinds of stuff. But like we don't have a lot of like very battery specific stuff yet,
Yeah.
and we're actually quite close to that. Like some battery cyclers and battery methods. We're just, frankly, we're a small company. It takes us a decent amount of time to get new stuff out in this way.
Yeah.
So I'll just put that once we have some of those, like once we have like a cycler out and we have some of the software stuff, I'm most likely going to do something. I don't know what, but I would love to. I mean, it's my personal discipline. You know, I love battery stuff. So I could probably make some videos on like how to calculate capacity and how to do some, stuff like that. So yeah, I'd love to do that for sure. I'll add it to the, the list of a million things that I have no time to do.
Yeah. Chris also mentioned it would be nice to have a feature in our software to do interval-based collection. And we agree. We actually spoke to our software engineer about that. It's not the highest priority thing, but
interval-based collection. What is?
Well, I think the idea is this is the kind of the what do we call it? The iterator concept. There's a lot of people who are like, instead of making like, oh, I want to do 1,000 cycles and then I want to collect data points after each 100, instead of making 1,000 cycles and breaking it up into hundreds manually, we had an automatic way to do that where like you select from a drop down and say, how many do you want? How many points do you want divided like per decade or something like that? We're working on stuff like that because people use that kind of scientists just think about like, oh, I want to do a scan rate study in cyclic voltammetry. Well, instead of making multiple CV parameters in an experiment,
you just want an iterator that says,
just iterate,
change my scan rate from this to this with these intervals.
Yeah.
Whatever. Yeah. So here's some inside information for you. When you work at a company, and you're what Alex and I do, we're in sales and we're PhD electrochemists. We want stuff and we say, can we have this? And the software team says no.
Yeah.
and sometimes we're like, I don't like that answer. And sometimes they're like, okay, well, I'll have it in you in like 6 years. And it's like, oh, well then I don't want it. So the reality of being at a company and also having software development that I've learned over many years now is that oddly enough, sometimes the things that you want that you think are easy take a really long time. It's bizarre. And sometimes the things you think that are going to be really hard, they're like, yeah, I'll have that this afternoon. And it's like, what?
Yeah.
How? That seems like it should be impossible. It's like, no, it's easy. But I don't know how to put a dot 2 pixels over. That's really hard. It's like, what? How is that hard? I don't get it. Yeah, software is a strange world, and they're strange people. I mean, I didn't say that. What are you talking about? Somebody's misquoting me.
Yeah, it's a process that we've learned about.
Collecting more samples. Oh yeah, so this is a good point. Actually, this is something that we are doing right now. In fact, there's a couple of experiments that we are like quite literally now implementing in a version of Aftermath coming up quite soon. This will be a thing. So an interval function allows collecting more samples early or late with sparser. Yeah. So actually one of the, to your point, Chris, exactly. This is for like, for example, for battery stuff. I always go back to batteries because it's my wheelhouse. But let me erase all this absolute lies about inductance. For a battery charge discharge curve, you typically have a shape like this. These are volts, and this is either capacity or time. We'll just call it time. You go up fast, and then you have a long plateau, and then it goes up here. So basically, you need a lot of points here to like clarify this curve, and then you don't need a lot of points here because it's like flat. So you take infrequent points, and then you need a lot of points here. So it's like what you really need is to like take a point every 2 millivolts or like 15 seconds or something, like whichever happens first. So here it's like, oh, it changed 2 millivolts in half a second. It changed 2 millivolts in another half a second. So I'm taking every 2 millivolts. But here it stayed at 1 potential for 15 full seconds, for like a minute even. And so basically you don't want to go too long without taking a point. But this is a common battery, and there's probably other just regular electroanalytical systems that benefit from this kind of, it's sort of like an invariant point selector, and it helps with what Race was talking about, or not Race, Ferris, about memory issues, because you don't have to take like it would be bad to take every half a second, especially here. Like there's too many points. You don't need it. It's not going anywhere. It would also be bad. So spread it out. Well, it'll be bad to spread out. You'd miss this whole curve if you spread it out too much in the beginning and in the end, right? You need this sort of dynamic kind of point selector, especially because this whole process takes 3 hours or whatever. It's like you can't have 3 hours with no points or way too many points. You want a sort of variant thing. So that's exactly what battery people commonly do, and that's what our software is going to do actually coming up.
Yeah. It looks like we have a question from Mawish again. Can you give some points on dissolution resistance for electrocatalysis or for electrocatalysts? But I don't know what dissolution resistance is. I mean, maybe
Dissolution resistance.
Have you heard of dissolution resistance?
I mean, I can infer from the title, obviously. I mean, if you're talking about the I think what I'm not sure about is if you're talking about if there's some phenomenon. Oh, Frank Sinatra was known as Old Blue Eyes. See, that's something I should have known. Thank you, Chris. Duh. Yeah, of course he was known as Old Blue. Yeah, I think somewhere in my brain I knew that. But then I'm like, oh, that's some other singer. I don't know. So I'll just talk about the Rat Pack. That's embarrassing. Here I am talking about music that I very much appreciate, and I don't even remember that he's known as Old. Yeah, no. I'm retiring right now. It's terrible. I don't even know who Frank Sinatra is anymore. Sorry. Does dissolution resistance? So, okay. So what I don't know if you're referring to is the electrocatalyst itself like dissolving? Is that, or are you talking about a dissolution of a reagent on the electrocatalyst and the resistance associated with it? Right. Those are two different things. And I don't know.
Yeah, I don't know. I have not heard of dissolution resistance.
I wonder if dissolution. I'm going to look it up and see if it's
question.
if it's a terminology I'm not familiar with. Selective dissolution resistance.
Photoresist?
Yeah, is it if it's a photoresist thing, that's a little bit different. Photoresist.
Look.
Dissolution process. I don't know if dissolution resistance is its own like phenomenon or thing that's dissolution resistance index. This is not something I'm familiar with, so I don't know that I can comment any further.
Yeah.
I'm sorry. I don't know.
For electrocatalysts, it looks like I'm getting like, how do things
Dissolution activation energy.
dissolve? Dissolution rate.
Yeah, I mean all
What
these
is-
things are like, again, like just we could talk about how things dissolve, right? And energy associated with it, or just
Right.
in some general way, but it seems like you're referring to a specific phenomenon. And I'm not
Dissolution
exactly sure.
has a corrosionpedia definition. So maybe this is dissolution
Corrosion.
is a formation of solution by dissolving solute in solvent. Dissolution refers to a process by which dissolved components, solutes, form a solution. Oh, this is okay. So that's just regular dissolution.
Yeah.
Just dissolving things. That's what it is.
Dissolution
But is there a resistance associated with it?
I mean, there must be in some sense, because actually this you ready for a segue?
Yeah.
Dissolution is a like it's like a physicochemical process, or just a physical process. I don't know exactly what you would classify it as, but it has some speed. Like some things dissolve faster than other things, so there's some kinetic, like a component to the speed at which things dissolve, which inherently means there's some resistance associated with it, because kinetics and resistance are tied. Do you see where I'm going?
I see where you're
You
going.
see where I'm going?
I
Yeah.
don't like it.
No, but it's good, because there's a question that you're going to answer from a previous one, and I'm feeding it. I'm lining it right up.
I know.
So the short answer is that we don't exactly know if this is a specific phenomenon or not. The slightly longer answer might be something related to the fact that if you're talking about dissolution as a process has a certain speed associated with it, that means there's some resistance associated with it as well, because it has kinetic properties, and kinetics and resistance are intertwined in some way. And Alex is going to tell you how that's the case based on a question from last week.
Yes. Yeah. I'll talk about a question from last week. Although when I think about things dissolving, it just reminds me of like solubility problems. And
I mean, if you just put like NaCl in water, it dissolves.
it dissolves.
Right? And it's like fast, obviously, because it's like sodium chloride.
There's an equilibrium constant associated with it.
Right, but it's mostly one way, because it like this is like this is like a KSP thing.
Yeah.
But again, this is like the difference between thermodynamics, equilibrium, and kinetics, because the speed at which a solid crystal of NaCl breaks apart to Na plus and Cl minus in water is pretty fast.
Yeah.
And so
It's
therefore,
got a large equilibrium constant.
yeah, so an associated resistance with it is probably very small. Like,
Yeah,
I
I just
guess.
never think of it as like.
I don't
in
think of it
terms
that way.
Resistance,
No, I don't either.
because
exactly.
resistance implies
Resistant to
electrical,
electrolytic.
electrochemical processes, but there's no electron transfer necessarily happening. Anyway, okay,
Yeah.
so
Well, we clearly don't know enough.
Clearly
So
don't
if
know
you have
enough.
any clarification of that process, you may wish, or if you have a paper or
yeah,
something on it, please feel free to give us a little more supplemental information. But we don't have any other input, I think.
yeah.
But anyway, that leads very nicely into this question.
Yeah, so Windstar last week actually asked a question. It was a little hard for me to understand what it was, but then he sent a follow-up comment trying to elaborate on it. And in a specific paper, here's the DOI, they determined the activation energy, EA, of different resistances in a lithium-ion battery. The rate constant of the Arrhenius equation was substituted by 1/R. And he tried to look this up and try to figure out where it was coming from, but he didn't find anything. And he wanted to know, really his question was what has to do with that. So I found the paper and actually had a chance to look at it. So if you do have questions ahead of time and you want to share, say, a publication, we can do that. So let me make sure I can show you this and share my screen. So this is the paper, and down here, let's see if I can zoom in. This is easy to see. He's looking at this guy right here, this equation. 1/Rx is equal to A exponent to the minus activation energy over RT. So it's the Arrhenius equation, where you have the frequency factor, the exponent, activation energy, RT, and Rx represents the resistance. And normally, when you look at the Arrhenius equation, this 1 over Rx is replaced with a K, a rate constant, where the rate constant of a chemical reaction is equal to all of this, right? The Arrhenius factor. So I did some looking, and actually in that book by Orizim, they do actually talk about this in the chemical kinetics section. So I'm going to unshare this so I can show you what I've learned. So let me just write this all down, because the question is, this might make it a little bit easier, but it's how do we get this kind of 1 over R related to K, where this is the the rate constant. So what I found, rate constant, can't write that quickly. So what I found that was interesting is if you look at Butler-Volmer kinetics, in Butler-Volmer kinetics, you have something like the current I is equal to the rate constant, times some E to the stuff. Usually there's a bunch of things, RT, but there's always, so I'm just going to put like some constant. I'm just going to call it A. But then there's a relationship between like E naught minus like the over potential. So it uses zeta or something. And this is like the general form. There, of course, is another, this factor here, A, has things like the alpha transfer coefficient. It has R, it has T. I think it even has like moles, stuff like that. It has all this stuff. But the important thing ultimately is that the current is proportional to this rate constant times E to the these constants, and then the difference between the E naught, the redox potential, and the over potential. So there's of course another form of it where this is kind of flipped, and if you push the reaction the other direction, the current will go the other way. So if you look at this Butler-Volmer form of the reaction, you'll notice that the current and the rate constant have a linear dependence from one another. And what people can do is, if you're looking now, this equation has to do with an electron transfer reaction, right? This has some kind of A plus electron gives you, let's just call it A minus, right? So you have your, oxidized and reduced form. So it's an electron transfer reaction, which means that when you have an electron transfer and you're looking at like a 3-electrode system, working electrode, we model it in impedance as the solution resistance, a Randall circuit. You have double layer capacitance, and then you have your charge transfer resistance. And this charge transfer resistance is a resistor, RCT. Looks like a P there, RCT. So if we think about this in a very simple way, just using Ohm's law, where V equals, oh God, what is with this line? Trying to draw quickly and describe things. If we just look at Ohm's law, V equals IR. If we know that this R is CT, then we should know that with an applied voltage, which in this case might be a sinusoidal voltage in EIS, at some DC offset, all of the current associated with the resistor associated with charge transfer is a Faradaic process. So it's all of this current that's useful in a kinetic experiment is related to, kind of follows this relationship. So if we look at it this way, if we solve for I, we know that it's voltage over RCT is equal to I. And the voltage in these experiments with doing EIS, let's say the voltage is more or less constant. We now have a way of looking at this inverse relationship between R, 1 over R, and the current. And because the current has a direct relationship or direct proportionality to the rate constant at a specific potential, then we can in a way substitute this 1 over R for K. And that is why you see this expression where you just substitute K in the Arrhenius equation for 1 over R. And I've even looked at a couple other papers where they plot things like 1 over R by the voltage, and they get these graphs that look like this, where the lowest resistance is this peak. I'm not so sure what they're looking for, but that's what I was able to find when it came to relating the Arrhenius equation, the resistance to to a rate constant, not necessarily the heterogeneous rate constant, but the rate constant, and then getting a activation energy from it. But at the same time, if we also look back at this paper, because now that I've seen this paper, I looked a little bit further into it, and I think that I described it for a charge transfer resistance problem, but they use it for all these other things. They're using it for all these different resistances that don't necessarily involve electron transfer, and they're kind of coming up with other activation energies. And I think that's okay. It's not how the equation was originally supposed to be used, or at least how it was derived. But perhaps I think it gives you some information about the activation energy if you use that kind of substitution. But so that's maybe my only comment about the paper. But that to my knowledge is where we get this 1 over R can be substituted for the rate constant.
It's kind of a funny thing because they're using this expression pretty liberally, right?
Yeah.
They're basically saying any resistance, like how you described it, is leading into that situation where it's really implied that it's kinetic information.
Mm-hmm.
And you have to guarantee that your results are kinetic only.
Yeah.
Because otherwise the current is not just kinetic current and the resistance is not just a kinetic resistance or whatever. And then you're sort of invalidating the use of that expression, the theoretical use of it. And so in some ways it's a misappropriation of the Arrhenius equation to make this connection.
Yeah.
Right. And also to me, it's funny because it's like, this is one of these things that's very paper academia focused and not much else. Pardon my dumping on on academia for a bit here, but like it's very academic and not extremely useful in my opinion. And maybe I'm missing a little bit of the details, and that may be the case. So admittedly, but it's like you're getting all these resistances, and then you can make this fancy table showing all of the activation energies from each resistor, like you pointed out. And it's like, oh, well, look at the difference in activation energy for all these things that aren't kinetic processes. But look, I just took 1 over and took the exponent and did a thing.
Yeah.
And it's like, you can also just compare the resistance values.
Yeah.
Like
that's right.
You just inverted them and took an EXP and calculated a different thing from each of them. You can, if you're trying to compare all of the processes or all of the phenomena to which each R corresponds to, just compare their values.
Yeah.
Like
Yeah.
you calculated a slightly different thing to compare it in a different way. But how instructive is that?
Yeah.
And it's to this point that like when I remember when I was in graduate school, even learning in the Arrhenius equation, it's like it became evident that for whatever reason, mathematically and empirically, it just seems like a decent amount of things, not even necessarily in just electrochemistry, just in chemistry, chemical engineering, they happen to like follow an Arrhenius like relationship for what it's worth. So it's like when it's like basically if you take anything that has a temperature variance and you plot natural log of 1 over t versus whatever the thing is, sometimes you get a straight line.
Yeah.
And that's an indication of an Arrhenius-like relationship. It's just like, right? Like,
Yeah.
like the Arrhenius, if you take the natural log of both sides, it's like you can plot natural log of rate constant or 1 over r or whatever, like, I don't know, like hair follicles, like whatever, like natural log of
Yeah.
anything versus the natural log of 1 over t. And you'll get like a linear relationship, and like there's a slope
Mhm.
that's proportionate to the activation energy, and there's an intercept that's proportionate to the pre-exponential constant.
Yeah.
And there's a lot of stuff that just like happens to work that way. So like, and that's actually like, I'm
Yeah.
fine with empiricism. Like empiricism is used to develop relationships all the time for calculating and predicting stuff. And like, there's nothing wrong with empiricism. It's just that like, if you're using empirical relationships that happen to resemble the Arrhenius equation, I think it's important to recognize when you're doing it as an empirical method
Yeah.
to help guide something, which is fine.
Mhm.
And you're doing it because you say, well, this means activation energy, whatever. It's like,
Yeah.
okay, maybe not so much, because that's a theoretical concept that requires the stuff that you just talked about, like kinetics and blah, blah, blah. So I want to sort of do that to differentiate between stuff that happens to work based on an expression, which is empiricism, and stuff that actually relates to that expression theoretically based on the first principles.
Yeah.
Those are different things.
Yeah. 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 No, I
There was a
agree.
question too from the very beginning that I realized that I wanted to answer and I forgot.
Oh, okay.
Bob Owl had asked this question,
Yeah.
like probably just before
Yeah,
sometime.
before we
So
started.
hopefully, yeah, exactly. I meant to answer it sooner because he seems to have asked it just before we started, and I didn't mean to skip over it for so long. So apologies, Bob, if you're watching this now or later. He says that in my Nyquist plot by, and I'm going to have to guess a little because I'm not entirely sure I understand the question, but I have an idea. In my Nyquist plot by EIS, the imaginary impedance decreases at high frequency and increases drawing a semicircle. What causes the decreasing line at high frequency, and how can I fix it? So I think what you're describing is something like the, oh, I got to share my screen. It sounds like what you're describing is what we typically call an artifact, or something like a high frequency effect that is, again, either you say artifact or something that is a result of typically the reference electrode. So it sounds like what you're talking about is that you have something like this. It's this kind of thing. It's like a semicircle that if it finished, it would be in like negative Z real, and this is Z imaginary, right? So this is negative Z real territory. This is 0. This is positive Z real territory, which is where most of your data exists. This kind of thing is a result typically of reference electrode impact. It's like,
Is this the thing we were talking about with the glass, or is it? Do you
yeah,
think it's separate?
yeah,
Okay.
I think it's related. So I'll try to describe this a little. I know it's like, how long do I want to go? I'll try to be
Yeah.
not like 35-minute explanation here, but basically we tend to call this artifact, and it's usually a result of the reference electrode. When you see something like this, the quickest and easiest option is to not delete, again, to clarify,
Yeah.
but to ignore. You can ignore this data and just start here for your analysis. If you're doing like fit, is to ignore this, because you don't want to fit a semicircle here, because there's no such thing as a minus R0. Like right, if you were to fit a semicircle here, if you were to have like Randall's element here for this first one, and then a leading resistor, and then another Randall's element plus a Warburg, if you're going to fit this, like this first Randall's element is inappropriate. Like you're going to get a negative ohmic resistance, and that means that your solution is like producing energy. Like it doesn't make any sense. Like it's an artifact. Even just visually, you can tell this. It makes no sense to have a semicircle that would complete in negative territory. It's not a real phenomenon. So your first two options are to ignore it, just ignore that data. Start at a lower frequency. If you're starting at like 1 megahertz, okay, well, instead that's supposed to be megahertz, I swear. MHZ.
Yeah,
Instead, start at 100 or 10 kilohertz, because probably these high frequencies is nothing of interest unless you're doing solid state systems. Most likely you should just start at 10 to 100 kilohertz, because you just don't need that high frequency information. It's pretty inaccurate anyway. Okay. But if you really want to, you can either employ a shunt, which is a whole thing. I have a whole video on a shunt. I won't get into it too heavily, but basically the way why this appears, I'll try to describe this phenomenon. I think it's a cool phenomenon. Alex and I just sort of like learned about it recently.
Yeah.
Actually, it's a really cool thing once you kind of figure out. And actually, someone recently told me, remember how we had the idea, pull the reference electrode a little higher? They said that it helped.
Oh, it did.
So it kind of,
that's
to
good.
me, it kind of confirms that that this is what it
Okay.
is.
Okay. Good.
All right. So one of the things that you don't see this a lot, I guess, like manufacturers don't always give this information, but if you look up like a reference electrode, typically it has this kind of a format, right? There's a frit here at the bottom. You have like KCl in here. You have a AG wire with AgCl, and this is glass, right? And it's in your electrolyte, your main electrolyte solution. And this is your whatever, H2SO4. I'm just making up stuff here, right? Here's your main electrolyte. Here's your fill solution, and here's your silver wire. Okay, great. And there's a frit down here. This frit probably has, let's just say, 1 kilo ohm of impedance. It's like a resistor. This frit is a resistor. All right. Now, if you look up information from a manufacturer on a reference electrode, I shouldn't say a lot of times, actually, it's not all of them, but people will say the reference electrode has a capacitance of about, was like 7 picofarads, something like that.
Yeah, 8 to 10 picofarads.
8 to 10. All right, I'm going with 7 because that's the first number I wrote.
Yeah.
And I can't erase now. It's too late.
It's close enough.
Yeah, whatever. Yeah, 8 to 10 picofarads, 7, whatever. It's a small amount of capacitance. Where does this come from? What does that even mean? It comes from the glass. Okay, so there is actually this situation here where you have electrolyte here on this side, you have electrolyte here on this side, and you have this separator, which is this glass. Glass is a very poor dielectric material, but it is a dielectric material. It has a dielectric constant and everything. So technically, there is a capacitance between the inside of the reference electrode and the outside. Now you'll notice one big problem with that is there is no physical communication, right? Like electrolyte can't go through glass. It's impenetrable, right? It can go through the frit. That's what the frit's for. That's the main purpose of the reference electrode in an electrochemistry experiment. There's actually ionic flow here, right? Ions move very slowly, not fast because you don't want heavy leakage. But generally speaking, ions plus or minus, right, K or Cl, can communicate in through this frit with a resistance of about 1 kilo ohm or so. But there's another way to communicate between inside and outside of the solution. It's through the glass. And it's this capacitance. Now, this capacitance of about 7 picofarads, if you do the math on this, basically at a high frequency, a resistor does not change its impedance, but a capacitor has a low impedance at high frequency. And so this goes back to this artifact problem. At about 1 megahertz, the impedance of a picofarad capacitor can drop below 1 kilo ohm. So at very high frequencies, what's actually happening is your potentiostat is following the path of least resistance, which in this case means that it is sensing through the AgCl wire and then through the glass. There's just nothing good about that. It's bad, but it's the lowest resistance pathway to sense at that frequency. At that frequency, it is preferred impedance-wise to sense through the capacitor through the glassware for a few short frequencies. Eventually, the frequency drops to 1 kilohertz, 10 kilohertz, 100 kilohertz. The impedance of this intrinsic glass capacitance or whatever goes up, and eventually it's higher than 1 kilo ohm, and then the potentiostat reverts to the appropriate pathway, which is through the frit. So this is why blocked frits are more of a problem, because it needs a pathway, and that if this impedance goes up, it's going to use the glass more, and that's bad because there's no communication. That's why you have this odd. Sometimes it like goes down, sometimes it's this way. You'll have strange behavior, but it's like artifact. It's not real because it's not like actual connection. It's like going through the glass. And one way to combat this is if you think about the capacitor, it's a function of surface area, actually. So if you raise the reference electrode out of the solution, you're decreasing the capacitance, right? Because if the whole reference electrode is like, this is your reference electrode, and it's like all in solution, you have a huge amount of surface area between the glass and the electrolyte. But if you raise the liquid level just to here, then all of this is not contributing to the surface area, only right here is. So you have a lower surface area. And if you look at the expression for capacitance, it's like distance over surface area over distance, whatever, right? It's like, it's proportionate to the distance between the two plates and the surface area. It gets bigger as the distance shrinks.
And the charge.
And right, yeah, exactly. And it goes up as the surface area goes up. So basically, one way to help fix this kind of artifact, which I've suggested, and someone once since told me, hey, it worked actually, is raise your reference electrode. Like some people don't think often; they just sort of dunk their electrodes in the experiment, whatever.
You're trying to get it close to the working.
So all that kind of stuff. It makes sense. You're trying to get it close to the working electrode. But if you're having artifact problems, raise your reference electrode high in the solution. Raise it above. It has to obviously still be in solution, but raise it as high as you can. You'll decrease the capacitance and you might have a better success.
Yes.
So that's my answer. Sorry it took so long, Bob. I meant to answer you sooner, but I just remembered that there's your comment.
Yeah.
So hopefully you'll see this eventually. And then, there's that. So it looks like Mawish was talking about the dissolution resistance. The point that he made was, it's written that palladium has smaller dissolution resistance than iridium in an acidic electrolyte. Oh, for OER. Yeah, I mean this. Let me see.
Yeah, this is the comment.
Yeah, it was written in Shan Wang research paper. I didn't understand, but it's okay. We make amazing videos. Well, of course. Yeah, thank you very much for the praise. I really appreciate it. Honestly, this comment just sounds like a different way of talking about that palladium is probably a better OER catalyst. Like smaller resistance means it's better. Like if it has less resistance, it does a better job. It's faster or whatever. So it just sounds like this is a difference or terminology to say that palladium is a better catalyst than iridium for doing OER, something like that.
Is there? Okay, I just thought of this. Maybe I'm right. Maybe I'm wrong. But like when something is dissolving in this case, like if I have palladium on the surface and it's dissolving into solution, it's got to be losing an electron, which means there's an electron transfer, right? Let's say you're going from palladium solid neutral to palladium plus or palladium 2, because that's what's soluble in your solution. So that's a Faradaic process. So maybe that's really what the dissolution resistance is. It's just another way for the Faradaic. And Moish, please let us know. It
says for OER. So I guess the question is it the OER, the oxygen evolution reaction? I don't know what the dissolution part is. That's where I'm getting. So it's like if you're talking about how the catalyst dissolves, like you said, during the process, then that's a bad thing. It means that palladium is like deactivating and dissolving more easily because it has a lower resistance. Yeah, it's interesting. I guess I'd have to see the paper and kind of learn more about exactly what they're talking about.
Oxygen evolution's an oxidation process.
Yes.
Correct. So it might be the case that iridium or palladium
is
oxidizing.
Yeah.
That might be what.
So maybe it's like palladium is bad
or is better because
it's worse because it's dissolving more. Like you don't want your catalyst to dissolve.
Yeah, that's right. That's right. You want to have a higher,
like for example, glassy carbon we said is terrible.
Yeah.
At OER. So sometimes you have to, like if you're using carbon, you have to go to, like you need a bigger overpotential. You have to go higher potential to initiate to drive the OER on carbon. And if you go high enough potential, you'll just start ripping carbon apart.
Yeah.
It'll oxidize. So there's probably a I think to me it's sounding like it's a discussion of the stability of the catalyst itself towards doing the reaction, and specifically with relation to OER, because you have to go to higher potentials to do it, you're oxidizing potentially the catalyst itself.
Yeah.
And so you would be interested in how much I'm oxidizing water or whatever to oxygen, plus how much I'm oxidizing my actual catalyst itself, which is a bad thing. One of those is good, one of those is bad.
Yeah. It's a separate. Yeah.
That all sounds
That makes more sense.
we figured it out.
It's like
I think.
it's like dissolution resistance for sodium chloride. It's like there's no electron transfer.
Yeah, that
Just
doesn't- yeah.
break it apart. But if you have a solid and it's oxidizing, and it's
Yeah.
dissolving. Okay, makes. I get that. I get
That sounds like
Okay.
what it is. Okay, I think we slowly got to the answer.
Yeah.
Hopefully
Slowly
that's- yeah. Here,
Okay.
Shabam's question.
Last question. Hello, guys. In CV curve, a point comes when the curve reaches net zero current, but non-zero voltage. What is the source of this voltage at the instant when the current is zero? It's a very good question.
Voltage is relative, my friend.
That's true. Yep. So that's one part.
Don't conflate 0 volts with 0 current, because 0 current means that nothing is flowing. 0 volts doesn't mean absolutely anything, because 0 volts versus what?
Well, yeah,
I think that's the short answer.
that's one part of it.
Right? Like you're assuming that 0 volts must mean 0 amps. That's a false equivalent.
Yeah. There are things to kind of think about with regard to voltage and zero current. So there are cases. So when you have you can in some cases have current flow when at zero voltage, just thinking about naturally occurring oxidation and reduction processes, right? So if I took a copper penny or something and I threw it in a solution, it's going to start oxidizing. You're going to have oxidation reactions because copper oxidizes very, very quickly. There's current flowing. But you know, but I'm not applying the voltage. I'm not applying some kind of voltage for the current to flow. And similarly, you know, you can have like an open circuit voltage, right? Is probably the best example. You know, there's an open circuit voltage between, you know, your two things, and it's a non-zero voltage, but in that situation, no current should be flowing in that circuit. And so that's kind of just like the potential difference between them. And then the other thing I want to mention about you very correctly mentioned that there's a net zero current. That doesn't mean that means that the positive and negative current that's actively flowing is net zero.
That doesn't mean there's no current, though.
Exactly. There could absolutely be a current flowing, but they're equal and opposite. So that's another thing to keep in mind.
Also, thanks, Chris. It looks like we lost audio for a bit. If there's something that needs clarification that we lost, please let us know. And then, Chris, you mentioned this. Would having thicker glass walls help reduce parasitic capacitance? In theory, yes. So those are the two things that you can, in theory, do to reduce that artifact. The problem is that one of them is easier than the other, right? It's like if you have your reference electrode, you can't like thicken the glass. I guess you could like build it up or something. But in theory, if you made a thick glass reference electrode, that would help also reduce parasitic capacitance.
Yeah.
But the easiest thing as an experimentalist is just raising it up out of solution.
Yeah.
So, but yes, in theory, if raising it up out of solution helps, then yeah, for sure, thicker walls would help because you'd be increasing the distance of that capacitor and its capacitance would decrease.
Maybe, I just think not that many people know about this kind of stuff. So like they should really be making thick reference electrodes.
Yeah. I mean, it's an interesting idea. Like, make like super thick wall. Maybe it has no parasitic capacitance because like if it's thick enough, there's effectively no capacitance.
Well, if you think about it, what if you doubled the thickness of the glass, it should half the capacitance. So you'd probably have to make it like 3 times to, you know, or something to kind of get it to that 1 or fraction of a picofarad capacitance. It's
doubling halves.
Yeah.
So I mean, if you have like a 2 millimeter thick glass, you do 4 millimeter thick, capacitance drops in half, and
Yeah. It would also make the reference electrodes more expensive, probably.
yeah,
You have a
thicker
lot more
glass makes them more expensive. That's true for sure.
And
Um,
and there's so many other problems with reference electrodes you're going to run into first,
yeah, exactly.
unless you're really doing a lot of EIS. But
Who does EIS? It's a terrible idea.
EIS with that technique.
That's a terrible idea. So like 7 picofarads, for example, at a megahertz is, oh, hang on. I have it here, basically. Let's just go look. Whoa, what axis am I on here?
You want to share?
Yeah, I
the
could
map?
share. Why not share? I could just look without, showing you what I'm doing, and then you just get to watch my face looking at my screen that you can't see. So for example, here's, I just used this convenient circuit here, but I made the resistor really small. So this is like just a capacitor, 7 pico. So you can see that's the red line, right?
Yeah.
What am I doing here? Well, let's home this. Where the heck am I? I lost myself. All right. Oh yeah, I don't need that. Why did I click that button? It's like I don't know what I'm doing, Okay. Let me zoom in here. I know it's hard to see this axis, even for me. I'm looking at my own screen. I can't even see the dang thing. 10 to the 4.5. So this is like, what do I got? I'm going to make this plot bigger. You can see the numbers showing up here. So this is 20K, right? 2.2, 10 to the 4. So basically 7 picofarads. This is like 20 kilo ohms. So this was a odd example. I guess if it's like 10, it's a little bit lower. Or what am I doing here? 10 picofarads.
I'm also looking at some of Chris's questions. He wants to know if the slight hydrostatic pressure change by raising the reference increases the diffusion rate through the frit slightly enough to matter. I kind of want to say no. I feel like adjusting the height of a reference electrode should not change the rate of diffusion through a frit. But I don't know enough about hydrostatic pressure.
Yeah, that's a thing.
Like any hydrostatic pressure also wouldn't be affecting diffusion because that's just the random motion of molecules. That would be hydrostatic pressure sounds like a convection type of thing.
Yeah.
So so hopefully that's just our opinion of it. And he also wants to know what the current thickness of our silver chloride reference electrodes are.
What the glassware?
Yeah.
I think it's it's like 2 millimeters. It's about 2 millimeters, I believe.
Yeah.
It's not the same everywhere because it changes at the bottom where it curves.
Yeah.
There's a taper when you do the glass that way. I think it's 2 to 3 millimeters thick, something like that.
Yeah.
In fact, I actually, after learning about this phenomenon, I calculated the 4 hours based on like a rough amount of depth or whatever, and I came up with like 8 picofarads, like right on where it's supposed to be. So here basically is the plot here, right, at frequency. As I increase the capacitance, it is an inverse relationship. So basically, if I go to like 10 picofarads for about some normal depth, some whatever, I'm at 10K. So like basically there's this is where the artifact basically comes from in theory, right? There's a short amount of frequencies where, I'm at 10 kilo ohms or even slightly less, depending on how high of a frequency I go to. And I'm in some sense could be less than the frit impedance for some period of time, depending on that. So it's like if I were to make this in half and go to 5 picofarads, let's say I make really thick glass, right? Take it out of solution. It's like I'm already starting at 40 kilo ohms. That's probably higher than the frit. So it's not going to, in theory, affect my results too much, etc. So that's the point. Also, it's not perfectly accurate because I I do have a resistor here. I shouldn't have a resistor. I was just trying to do something quick to kind of get a
Oh yeah.
get a number. My recollection was that it was like 5. It looks like it's like 10. Anyway, whatever. It's in that ballpark. It's 5 to 10, kilo ohms or something like that. So
Yeah. Let's see. It looks like we have a question from Ian. Ian, do you have any general advice for performing LSV experiments in PEM fuel cells? Is there any significance the voltage at which peak current is achieved? Significance? Is there any significance the voltage, maybe to the voltage at which peak current is achieved? I think we talk about. I felt like we talked about PEM fuel cells earlier. Like one of the first questions I thought we got had a little bit to do with performing LSV. Let me take a quick look because I felt that we talked a little bit about it. Maybe I'm wrong. Let's see.
LSV experiments with PEM fuels. So I'll give you some advice on LSV experiments with fuel cells. Very slow scan rate.
Do OCP first.
Yeah, well, you run OCP, so make sure your fuel cell has a volt. If you're doing a PEM fuel cell, it should be about a volt. The theoretical is 1.2, and most likely you won't get that, but you'll get 1 or 1.1. And then typically you're going to do an LSV experiment from open circuit, which is 1 or 1.2, down to about 50 millivolts. Go slow. In fact, some people don't even do LSV at all. What they do instead is a series of chronoamperometry. Because what you're really doing with a fuel cell is you're like dropping the voltage down to see how much current you get out of it, right? And so you actually want to get more of a steady state. Sorry, it's typo. As in, is there any significance if one LSV run has a peak at 400 millivolts, another? Okay, so I'll finish my thought because this is just about getting the data at first. Right. So scan very slowly. You can go like 1 millivolt per second slow, like painfully slow, 5 millivolts per second fastest maybe. That's a quick and dirty way to get like your polarization curve for your fuel cell. Again, it takes a little while. Or do every like 5 millivolts, do like a 10-second CA experiment. It's also a bit tedious. But you're just sort of stepping the potential down, seeing what the steady state current is, stepping it down. And then when that's all together, you plot your steady state current versus the potential, and you get a pseudo LSV curve, but it's like a little more, you're taking some diffusional, capacitive effects out because you're not scanning really fast. When you scan faster, you have more capacitive effects. And so you kind of take some of those out. And then, the second part of your question, significance to where the peak current is achieved. One LSV run has 400 millivolts. Another has on the same cell. Well, I actually, So part of this as well, maybe you can clarify, like, is this a full fuel? I was just, all the advice I just gave you was assuming you're working on a fuel cell, like a full fuel cell. If you're looking at the material as a half cell, then it's a little bit different. If you're looking at like a half cell material that you're trying to study just the oxygen production reaction or just the hydrogen oxidation part or whatever, that's a little bit different. Then in that case, you don't necessarily need to go so slow. I'm just talking about the full fuel cell. And if you're getting a different peak, like with the same cell and different stuff, I mean, it might mean that something is changing. Like you're either activating or deactivating. Like in a vacuum, I don't know whether that be, whatever situation you're looking at, if that means that the peak position is getting better or worse, like is the overpotential decreasing or increasing? If it's getting better over time, it means you're probably activating your catalyst in some way, or you're like it's the same way that you do like multiple CVs before you start to like clean the surface and get a fresh surface and do that kind of thing. That might be what's happening. Or it's the other way. If it's getting worse based on what you're looking to see, you might be like your catalyst might be deactivating or something. Otherwise, again, there's just a lot of possibilities here because it's a fuel cell. If it's like single MEA with H2 on the anode and N2 on the cathode to measure hydrogen crossover. make sure the streams are humidified. If you're having inconsistencies, it might be dehumidifying. Make sure, the fuel cells are notoriously finicky and a pain to deal with because there's a lot of stuff like the membrane needs to remain humidified or it doesn't really conduct very well. And that could be affecting your results. Make sure the temperatures are steady. There's a lot of stuff. It's hard to think of other specifics without seeing the data, but those are just a few things that come to mind. If you're doing two tests and they're two different results, it's like, first of all, welcome to electrochemistry. That's sort of natural. When you do 100 of them over 2 hours, what does it look? Is it all over the place and completely inconsistent? Like, then something strange is going on. But if it's all kind of oscillating around a similar point, then maybe that's just, in the signal to noise, right? In a vacuum, just two different points at two different values is like, I kind of don't know what to say exactly to that, right? But those are just a few thoughts I have based on my own experience doing fuel cell stuff that I guess I would tell you without seeing the data and knowing any more. And yes, Yuri, please ask your questions, but do it fast. Type like the wind. We're just about done here. We usually go about 2 hours and not too much longer.
Yeah.
We can hang on for a minute while we wait.
Yeah. That's fine. How
does scan rate impact capacitance and supercapacitors? It shouldn't.
Yeah.
When you change the scan rate,
whoops, for CV.
Yeah.
Yeah, the capacitance doesn't
shouldn't change the capacitance.
Shouldn't change. The current you measure will change.
Yeah, exactly. If it does affect it, you've got a different situation, like some pseudocapacitance or pseudo reversibility or some sort of different situation, right?
Yeah.
In theory, the scan rate should not impact the capacitance. Like Alex said, when you scan faster, you get higher current.
Yeah.
And then eventually you can correlate with the capacitance. But again, it's in theory, because in practice, nothing ever works exactly perfectly, because this is electrochemistry and this is science more broadly. But in theory, it shouldn't.
Yeah. So the relationship is that the current is equal to the capacitance times dV/dt, the scan rate. So if the scan rate increases, the current will increase, but the capacitance should remain the same.
Yeah.
Yuri is actually mentioning Joe recommended us to the channel. Well, thank you, Joe.
Which Joe?
Yeah, Joe's a relatively common name.
Yeah, we know some Joes.
We know a couple Joes.
What's maybe you don't want to give too much information, so we don't want to dox anybody here or anything.
And he knows us personally.
He knows both of us personally. Which Joe knows us personally?
It's Joe, the owner of the company.
Yeah, the owner of our company is named Joe.
Yeah.
I don't know if it's him.
He knows us personally.
He does know us personally, though.
He does know us personally. That's really it.
Yeah.
But he never mentioned, like, hey, Alex and Neil, I know a guy named Yuri who would love your YouTube channel. So
yeah, I mean, thanks, Joe, whoever and wherever you are.
Yeah. But yeah, if you want to ask us
ask us a question, but more importantly, who's Joe?
Yeah, who's Joe?
I'd like to know who Joe is.
You can even, if you don't want to give a last name, you can say like, all right, well, like what university or
where,
what
maybe we would remember. Yeah.
You know, maybe we know him back from Nam. I don't know. Joe from Nam.
Joe from
or something like that.
Probably not from Nam.
Not from Nam.
I think we have one definite place that we know we don't know Joe from. That's the only one. We know him from the darkness.
Joe Mama, yeah.
Joe Mama.
But Tish. Yuri has jokes.
Yuri has our sense of humor.
Yeah, that's right. That's right.
I missed your previous question. I thought we covered Race's question. What
do we not? Let's
hang on. Let me look, Race. Wait a second. It was not intentional. There's a lot of comments.
Yeah. Okay. All right.
So, the Kramer's Kronig thing. I'm sorry.
Oh,
I did see it, and then we missed it.
Yeah. We totally missed it. Do you want to?
Yeah, I can try to talk about this.
Talk a bit about it.
It appears that through adjustment of time constants, we can validate nearly all data using the Kramer's Kronig transformation. if that's the case, how reliable can we consider the Kramers-Kronig transformation to be? So first of all, I'm not sure I fundamentally understand, because if you have impedance data that has some time constant and then you change that time constant, that doesn't make it not impedance data. So I guess maybe I don't understand what you mean by adjustment of time constants. Like, having different time constants or adjusting time constants doesn't fundamentally mean you're like making non-impedance data, unless I'm not understanding that phenomenon correctly. So that's the first thing, right? Yes, I can read his full name, Chris. This is a PG show, so I'm not going to read the full name. Thank you very much. Do you see Yuri's full name? Don't read it. Read it in your head.
Read it in my head.
Yes. Do you get it?
Yeah. I'm reading it in my head though.
Yeah. It's not a real person.
Yeah.
He's not Russian.
He's not Russian.
No.
Yeah, I was thinking
his name is hilarious.
Yes.
If you're in 3rd grade. Okay. Sorry. Okay, so first of all, that's my first point, is that adjusting the time constants, like changes like on the Nyquist plot, for example, like the shape of the semicircle or something, that doesn't like change it from valid to not valid impedance fundamentally, I guess. For instance, KK transformation uses Voigt or Maxwell circuits. I don't know Maxwell circuits. Maxwell circuits.
Maxwell circuits.
The other thing that I would say, I know Maxwell's equations is the whole thing. I don't want to get too heavily into this. Maxwell circuits. I don't. This is getting a little more complex. I think that's where it's like, oh yeah, it's like you have a square thing. That's a bit more wonky and is somewhat outside the scope of electrochemical impedance, like regular impedance of regular circuits. People do on all kinds of electrical circuits, including different ones like that. You don't often see a lot of that with the electrochemistry data. I guess what I would say, without knowing exactly the answer to my last question, which is to say, like, okay, well, changing like a faster or a slower reaction doesn't mean that it's not impedance suddenly, which is what KK is testing for. The one thing that I will say is that because Kramers-Kronig is purely mathematical, it is much more susceptible to false positives than false negatives, which is to say it is possible in some cases that Kramers-Kronig can tell you it's good when it's not good. It's much less likely that it tells you it's bad when it's actually good. So if Kramers-Kronig says it's bad, it's really probably bad. But it is possible for Kramers-Kronig to say this is good and it isn't good for other reasons, because it's purely mathematical. And the easiest example to give is negative resistances. Just like that artifact I talked about, or some other strange phenomenon. Like if you have negative values or something strange like that, Kramers-Kronig is mathematical. I'm not sure if you're aware of this, but some numbers are negative. So yeah. So but for real, right? It's like if you have negative values, like negative resistances or something, it makes no sense physically. And so that probably means your impedance isn't like valid. But Kramers-Kronig will just be like, oh, sure, it fits. So it is fundamentally more possible and more likely, I would say, that Kramers-Kronig can give you a false positive, like a false indicator that this is good, than the other way around, which is to say, like, it's not as likely that it gives you a false indicator that it's bad, but it's actually good. So perhaps that answers your question. Again, with the caveat that I don't totally agree with the premise, or at least understand the premise to a certain extent. But if you're getting KK that says it's all good every time I do something wonky, that yes, it is possible that it's giving you like a false positive and it isn't actually good. That is possible. So there you go. And I think with that, we're good.
Yeah, I think we're good. I think we've answered all the questions. Yeah, thank you all for showing up. And I won't be here next week, but following week.
I guess it'll just be me.
It'll just be you. See you
I guess
next
that's
week.
what I get for ditching you last week.
Oh no, no, hardly.
Yeah.
But all right. Well, thanks for stopping in, guys, and this has, I think, been a great and educational episode.
And thanks again for Chris for being our surrogate answer when we're blabbing on about something. Chris
Yes.
is answering other people.
Yeah.
So
yeah.
much appreciated.
Yeah, much appreciated.
Yeah.
All right. Have a great
Yeah.
weekend, and
Yeah.
we'll see you.
Take
next
care,
time.
everybody, and I'll see you next week. Same bat time, same bat place. Is that what they used to say in Batman?
Yeah.
Is that a
Yeah.
thing? Yeah, that's what I thought.
Same bad times.
Like
yeah,
the
I think
old
so.
Batman. The old Batman ones, right?
Oh
Like
yeah.
Adam West
The Adam
Batman.
West Batman. That's it. Yeah.
Same bat time, same bat place.
All right.
Sorry,
Have a
that's
nice
so
day,
cheesy.
everyone.
All right.